Our group has worked on network intrusion detection using machine learning. We implemented and optimized 8 different algorithms focusing on improving their performance. For each model, we evaluated key metrics such as accuracy and F1 score to measure how well they detected intrusions. For the original KDD dataset, we used the SVM model and obtained decent results. Here, the scikit-learn implementation actually outperformed the Scratch version. With proper hyperparameter tuning, it delivered even better classification accuracy. Hi, I'm Kaustubh and I worked on the SVM algorithm. For the NSL KDD dataset, we built a linear SVM model from scratch which achieved an accuracy of 90.1%. To improve its performance, we applied hyperparameter tuning and the SMOT technique to handle class imbalance. These steps significantly enhanced the model's ability to detect intrusions.
I'm Satvik and I implemented KNN using scikit-learn. I tuned hyperparameters like the number of PCA components and K value on the validation set for both Euclidean and Manhattan distances, visualized through heat maps. The best results came with Manhattan distance, 40 PCA components, and K equal to 1, achieving 99.81% accuracy and an F1 score of 0.9976 on the test set. Similarly, on the NSL KDD dataset, the best results are with alpha equal to zero point 0.1, 500 epochs, and a threshold of 0.54, achieving 72.26% accuracy and an F1 score of 0.6957.
I trained a decision tree model using both the approaches of sklearn and custom implementation. I got very high accuracies for the KDD Cup 99 dataset, which led to the fact that the dataset was skewed. Then after I trained the same model on the NSL KDD dataset, I achieved an accuracy of 81.46% and an F1 score of 0.8111. I also used hyperparameter tuning to achieve better results. The parameter used were maximum depth of the tree and the impurity used.
This slide shows Neighbor's performance on KDD Cup 99 dataset. Both models achieved 97.37 accuracy and an F1 score of 0.9665. ROC curve with AUC 0.98 highlights strong classification ability despite the dataset's imbalance. Here we evaluate Neighbors on NSL KDT dataset. sklearn gave 88.68% accuracy with an F1 score of 0.8691. The F1 versus alpha plot helped the best smoothing value, while the ROC curve showed decent performance overall.
For the KDD Cup 1999 dataset, I applied random forest fit to 30 estimators. The model achieved a near perfect 99.98% accuracy and F1 score. However, this high performance is due to the dataset's heavy class imbalance and duplication, which makes it less ideal for evaluating real-world detection problems. To address this issue with KDD dataset, I used a more balanced NSL KDD dataset. Accuracy dropped around 78% and the F1 score was around 0.7739 using scikit-learn and 0.77 from a Scratch implementation. This shows the model generalizes better and is not memorizing patterns, making it a more realistic for real-world detection.
I worked on an artificial neural network for an intrusion detection system, focusing on its architecture and performance tuning. On the KDD Cup 99 dataset, the model achieved 99.72% accuracy with an F1 score of 0.9964, though this was due to the dataset's redundancy and imbalance. On the more realistic NSL KDD dataset, it achieved a 79.98% accuracy and a 0.7909 F1 score. I hyperparameter tuned the learning rate and threshold. The best learning rate was 0.001 and the best threshold was 0.5.
XGBoost is an efficient gradient boosting algorithm used in machine learning for classification and regression tasks. I used the scikit-learn wrapper of XGBoost and fine-tuned its hyperparameters on the KDD Cup 99 dataset. As a result, I achieved an impressive accuracy of 99.94% and an F1 score of 0.9993, showcasing its strong performance for intrusion detection. Similarly, on the NSL KDD dataset, I performed similar hyperparameter tuning and achieved an accuracy of 80.74% and an F1 score of 0.8016. I am Satvik and I implemented the logistic regression algorithm from scratch. I performed hyperparameter tuning on the validation set, experimenting with the learning rate alpha and the number of epochs, and visualized the results using a heat map. The best alpha was 1 with 2000 epochs, and the optimal decision threshold was 0.31. On the test set, the model achieved an F1 score of 0.9875 and 99% accuracy. Similarly, on the NSL KDD dataset, the best results were with alpha zero point 0.1, epochs 500, and the threshold as 0.54, giving a test accuracy of 74.32% and an F1 score of 0.7256.